has two parts here. First part here says that if my function f is continuous on the interval a to b, then the function capital F of x is equal to the integral from a to x of f of t dt, has a derivative at every point x in that interval a to b, and the derivative of that big function f is equal to the derivative of that integral from a to x of f of t dt. That sounds super confusing, and it doesn't make any sense until we put some numbers with it.
I'm missing you.
He should be back next period, I think.
Why won't you?
Well, you
Sorry.
need to first or keep.
No, I don't think they're supposed to get done till 11 or 11:15.
Wait, will he be in 7
But if you're
hours?
talking to him right now, he's going to hear you when he watches this video.
Oh, Liam, I love you.
Yes, he should be in 7th hour.
He will be in 7
He's
hours.
not
Okay.
gonna watch the
Yeah.
video.
So
He might, you never know.
I'll tell him to watch it.
This is way too
Okay.
No, he's in his assignment.
We do have a second portion to this fundamental theorem of calculus. Yes, we do.
I'm gonna need to get off the conference.
Are you gonna pay the money that you did?
No, yeah.
$30.
Yeah, I paid like the $40. But switch yes.
For what day?
Another day.
I'm working today.
What the?
Remember it's your birthday.
Who cares about?
Well,
And then this is the part that we have already been working on. So part 2 is what we've already been doing, which says that the integral of little f from a to b is equal to big F solved at b minus big F solved at a. So if we take the antiderivative of the function that we've been given, solve it at our interval endpoints, then we have our answer for the area under that function. This is what we've already been doing. The first part is the new part that we're going to do 4 examples on, and then you're going to start your review. So really the only difference between what we have been doing and what we're going to be doing now in part A is that part A up here has a variable x on my interval and my variables don't match. So you're going to see what I mean in a second.
Roll a little bit.
Up or down?
Only up.
Check it.
I got everything on the divisive
I lied, there are 5 examples. Would you like 6, Rotary?
Are they long examples?
No, not at all. Okay, so first example. Asks us to find the derivative of y. So y here is equal to the integral from 2 to x of the function 3t plus cotangent of t squared dt. Yes, 2 to x.
I hate when you
I hate T's.
Because I mix it up with the plus sign.
That's why I curved my t's.
Yeah, but like I
You should
know.
just never put T's in it.
Oh, they're gonna have t's in there, I promise.
That's like change sleep.
I'd rather have a t than an s, because then I start thinking they're 5s.
Yeah, that too. Yeah, use like something.
You see, I don't know.
Like R.
But z's can start looking like 2s.
No, they can't. We're gonna see, are you right?
Not mine, other people's.
Actually, your 2 looks like a Z.
Use a V.
We could use e. That doesn't look like anything. Okay,
Yeah.
so what I have here is I have the little f function that is 3t plus cotangent of t squared. And I have the interval or integral from 2 to x. And I would like to take the derivative of this function in terms of x. If I were to just take the derivative of it how it is right now, it would be in terms of t because that's a variable I have present. So what we need to pay attention to is the fact that the variable x is currently in my integral, which means somehow I'm going to have to plug it into the function. This is where Leibniz's rule comes into play. I'm sorry.
It's the tag in that.
I've never heard that before in my life.
Leibniz's rule says that if I have a variable in my integral, to solve the problem, I plug the variable into the function and then multiply by its derivative. And then that's it. So dy dx here is going to equal 3x plus cotangent of x squared all times the derivative of x, which is 1. That's it. And then, of course, we simplify it out, and it just becomes 3x plus cotangent of x squared. And now I have the derivative in terms of x.
Wow, that's it?
That's it. Huh?
What?
The derivative of x is 1.
I'd like to, I'd like to see you.
I don't like how that squares inside.
Well, it's x squared, not
Yeah.
cotangent squared. Okay, how easy was that? Let's do another one.
Wait, so what do we do with the t?
Nothing, the t
I
disappeared.
meant the
I
t.
replaced it with an x.
The
So
t.
wait, don't we have to like multiply something into that?
No, this is, we're done.
What's that?
What are we doing with the T?
But-
I mean, the 2.
So we're not finding area?
What is going on?
That's not the main purpose here.
But why is the 2 there?
Right, okay.
I'm cold.
So this is the key. The way we've been doing this before is that I plug the top one in to the antiderivative, right? And then plug the bottom one into the antiderivative and subtracted the answers, right?
Yeah.
So if I follow Leibniz's rule, when I plugged x in and multiplied by the derivative, I should have then plugged 2 in, right? That's what you're telling me. Hold on. And then multiplied by the derivative of 2, which is what? So this whole second function disappears anyway, leaving just that first function. So that's the key that Leibniz picked up on. I'm going to show you what happens when we have 2 variables.
Okay.
We're just not there yet.
Oh,
We're slowly easing into this. Let's do another one.
That is really
Can we cut this tag off?
We will in a second. Let's do this first.
I have never, I have never noticed this one. And it's really making me mad.
Oh, gosh.
Like, it's all I can think of. Like, it's really fun.
Is that a u?
That is a u.
Man, I wrote a 4.
So here, y is equal to the integral from 4 to x of e to the u times secant u du. This works the exact same way as the way before. I notice that my x is on the top, which is where I need it to be. I go ahead and I plug that x in. And I multiply by the derivative of x, which is 1. And then I'm just left with e to the x secant of x.
That's it.
That's it.
Wow.
How do we like this?
How many are there? 5?
We're doing 5. We're already down 2 down.
No, but like, what if we have a variable on the bottom?
Okay.
There's 2 variables.
Okay. We're getting there. Next example. Kind of jumping the gun there. You're right. I
That's
can't.
a 6, not a B, right?
Ah.
Wait,
No, the negative.
is it a 6 or a B?
I think it's a 6. I think she went.
It's a 6. X squared to 6.
Negative.
Wait.
There is a negative in front of the
is
integral.
sign just gonna flip?
Hold on. There is a negative in front of the integral. This doesn't really, it does work, it just gets a lot more complicated if my variable's on the bottom of my integral. So I need to flip my integral, putting the x squared on top. What do I know happens when I flip the integral? The sign on the front changes. So since it's already negative, it's going to flip to a positive. So this is going to become the positive integral from 6 to x squared of cotangent of 3t dt. And then I work it just the same.
I was thinking, if you did the 6, you just get 0, and then you get minus.
Right, so it's going to do the same thing, it just gets a little less it gets confusing from here.
Oh, no.
Okay, so now I want dy dx of that. What am I gonna do, Tiana?
You are going to cotangent of 3x squared times 2x
Y times 2x.
because that's the derivative of x squared.
That's a derivative of x squared. We don't like stragglers at the end after a trig function, so I'm just gonna move that bad boy out front and then I'm done. Two more.
It's really quick.
Sorry, I can scroll up.
It's for Liam.
It is for Liam and Erin, yeah, if she decides to get on.
As that too.
Oh.
I definitely counted her absent because I didn't think she was at ASVAB, so I will fix that.
She is in that one. Because she.
Did you guys see her
was on
haircut,
leader,
though?
so she didn't take ASVAB one. So she's taking.
She's already taken it.
Or did she take? Well, actually-
She passed it, she said she passed it.
Yeah, but she wanted to take it.
Oh, okay.
Oh. Erin's weird.
Yeah, Erin's weird.
Erin, what a weird. She cut all her hair off.
I haven't seen her yet.
She put some,
I haven't seen her in person.
yeah, why can't together? It's really cool.
So now we've hit the case where I have a variable in both the top and the bottom.
It's a little bit more.
Is that a plus or a T?
That is plus, 2 plus.
Letters in math are stupid.
Agreed.
There are 2 ways that we could look at this problem. There's the way that we have been doing where we only allow the variable to be on top, or we could go the full Leibniz rule where I do integration like normal and multiply both of them by their respective derivatives. I think that's gonna be the easiest for you guys, so that's the way I'm gonna do it. So Leibniz's rule, just like we showed in the first example, says that I just plug each of these interval endpoints in and then multiply the answer by the derivative of that specific endpoint. So when I do that here, I'm going to have the natural log of 2 plus my top endpoint 5x squared times the derivative of 5x, which is 5. So I just plugged 5x in and multiplied by the derivative. And then minus the same thing with the 3x squared plugged in. Times the derivative of 3x squared, which is 6x. So I just plugged the top in, multiplied the answer by the derivative of 5x, then minus, plug the bottom in, multiplied by the derivative of 3x squared. And now from here, we're just simplifying. So of course, I want to go ahead and square out the 5x and then multiply the 5 into it out front. So this becomes 5 times the natural log of 2 plus 25x squared minus 6x times the natural log of 2 plus 9x to the 4th. Right, I just squared some stuff and moved some stuff around. When we have more than one natural log and there's subtraction involved, I know I can only simplify this down to one natural log. So we need to use our log properties that we learned. The first log property we have says that any number multiplied into the front of a log was originally an exponent. So this becomes a natural log of 2 plus 25x squared all to the 5th power.
Where did that come from?
Same thing, it's a log property.
I've never heard of that in my life.
And the second one becomes natural log of 2 plus 9x to the 4th all to the 6x power.
I feel like math is just like making random stuff up.
The last simplification says if I'm subtracting 2 logs, that can be rewritten as division inside of 1 log. So this becomes a natural log of, this one is my numerator, so 2 plus 25x squared to the 5th divided by, and then that one is my denominator. And then we're done. This is real. And then we have one example left and then we're finished.
Does anyone actually pass the AP?
Yes.
How often?
There's not a huge percentage that get like 4s and 5s, but
Like, you know what, it's fun per year. Does someone pass every year?
I've only been teaching this 2 years,
And
So
and last year doesn't count.
Oh yeah, last.
okay, how
Because
many
last year was atrocious.
How many passed your first year?
I had 2,
Out of
7.
okay, you know what, it's fine because I'm gonna take it again next year and I'll just
Wait, why are you taking it again?
and
In college, she's talking.
Oh.
I'm gonna be
And I have gotten a lot better in like this class since then.
good. That's all I want.
What's
So
what
do
you
you
want?
think
A whole
we
page
won't even
dedicated
get a
to
cheat
super
sheet or anything, will we?
That's
Huh?
how I
We
want
won't get a
You don't
cheat
get
sheet.
anything on the AP test.
Yeah, we're
Anything at all.
gonna
So that's why I'm hoping they really do go back to that original format. Okay,
Yeah, he doesn't even deserve his picture.
last one, and then you can work on your review.
That's so embarrassing. Literally, that's so embarrassing. I'm happy to see you.
Will he get his own? Oh yeah, he does get his own section, right? Never mind.
Oh, but now we got like a whole new thing going on.
No, it's just a different way of looking at it. Are you gonna be okay, Deanna? Okay, so the first one asks us to find the derivative of f, which means I'm going to be dealing with that integral. This is the same as dy dx. I want to find the derivative of that integral. I know it has a variable in the interval, which means I can use Leibniz's rule, which says that I do what with that 3x? Plug it in and then multiply my whole answer by the derivative. So f prime of x here is going to be the square root of 4 plus 3x squared, all times the derivative of 3x, which is 3. Of course, I do want to simplify that so it looks a little bit nicer before I move on to the next portion. So I can write this a little bit nicer as 3 times the square root of 4 plus 9x squared. Not much nicer, but it's a little bit nicer.
Oh.
Yes, ma'am.
I don't know.
Okay.
I didn't know why this was still squared. I understood the time, but I thought it
Okay, so remember, this is f prime of x. So now what I need to do is I need to find g prime, which means I'm going to be dealing with that function over there to the right. It told me that original g was the function f with sine of x plugged into it, which means that g prime has to be the derivative of f with sine in it times the derivative of sine, which is what? Cosine. So I'm going to take this nice, pretty derivative function that I already calculated. I'm going to plug sine into it, and I'm going to multiply the whole thing by cosine. So 3 times the square root of 4 plus 9 times sine of x squared And then all of that times cosine of x. And then we just kind of move stuff around, make it look a little bit nicer. So this becomes 3 times cosine of x times the square root of 4 plus 9 of sine squared x. And that's it. The important part here is that we use the first derivative to create the second derivative.
Okay, we don't have actual.
Your actual homework is to start working on the review. Less, 20 questions or less. I can't remember exactly how many I put on there. This is for your test, which is Friday.
Means it's optional.
It is not, well, if you do all of it, you get extra credit again. And it's worth a homework grade. So I definitely suggest you do it.
And then do we get one full?
Okay, so for your cheat sheet, you get